Welcome to the section on performance measurement. One of the most popular performance measurement metric used in object detection is a mean average precision. Supposing we have this image where these are the actual bounding boxes and then these are the predicted bounding boxes. Then we have another image like this where we have the actual bounding boxes, this the predicted bounding boxes. So here we could see that the predicted bounding boxes actually get the two persons, but here we only predict the aeroplane almost accurately, whereas with this predicted bounding box doesn't align with the actual bounding box, and with this bounding box there is actually no predicted bounding box. With this other bounding box for the smaller aeroplane there is no bounding box. Now we are having two classes, so in this case we have person and aeroplane to work with. In our example we have been working throughout with 22 classes, but with this, for this example, for the sake of this example, we shall use just these two classes, person and aeroplane. Now the mean average precision is actually calculated using the precision and the recall, which are both metrics we had seen previously. For precision, it was defined as the true positives divided by the true positives plus the false positives. And for the recall, the true positives divided by the true positives plus the false negatives. Now, what's a true positive? A true positive is an actual prediction, or rather, is a prediction which is actually a correct prediction, like in this case, for example. Whereas a false positive is a prediction which isn't an actual prediction, or which doesn't surround any object correctly. For false negatives, we're actually talking about the number of times we actually don't predict a bounding box surrounding an object. So in this case, we could count this as a false negative because there is no bounding box predicted that surrounds this. For this smaller aeroplane, there is no bounding box, and then for this person, there is actually no bounding box. Now note that these values are actually calculated depending on a certain threshold. So we define the mean average precision at a particular threshold. So in this case, we're supposing we're working with a threshold 0.5. Now if our threshold was very small, like say 0.00001, then surely these two bounding boxes, we could say these two actually have an IOU greater than a very small number like 0.0001. In that case, we could say this is a true positive. But once we're working with this threshold of 0.5, it means the IOU between a predicted and an actual box must be greater than 0.5 before we could say that this prediction is a correct prediction. Now another important point to note is that the mean average precision is the mean of the different average precisions for each class we're working with. So it is not like we mixing up all the classes and then calculating the precision and then looking for the average precision. That isn't actually how it works. The way it works is that we look for the average precision for each and every class. So for example, we have the class person, we work with the person first, we find its average precision, and then we move to the aeroplane, we find its average precision, and then the average of that gives us a mean average precision for a particular IOU or particular threshold. Now let's get started. We now move for each of the predicted persons, since we're working with a class person. So for each of the predicted person, or anywhere we have the object class corresponding to that of a person, we actually go through each and every one to calculate the precision. So let's start with this first prediction. For this first prediction, we have a precision of 1 divided by 1. Reason being that it is a true positive, and the false positives for now is equals 0, because if we're supposing that this is our only prediction and then this is the actual prediction here, clearly this IOU between this predicted and this actual is greater than 0.5. So this is a true positive, and for now there is no false positive, so we have a precision of 1. We move to the next image, or rather to the next object instead. So we're working with the next person class. For this other person right here, we have an IOU of greater than 0.5. We could see clearly that the IOU between this and this is greater than 0.5. So for now we have 2 true positives and no false positive. Moving to the next person, which is, or the next prediction for a person, which is this prediction right here, we have an IOU which is less than 0.5. So we suppose that this is a false positive. This is meant to be a positive, but actually, as we could see right here, it isn't, or the IOU between this and this isn't greater than 0.5. So we consider it to be a false positive. So in that case, we have 2 divided by 2 plus 1 false positive, giving us 2 and 3. Now, as we calculate the precision values, we also calculate the recalls. For the recall, at each step, we simply look for the number of times we don't have a prediction for a class or for an object class which corresponds to a person. So for the first time, once we have only this, we suppose we have only this prediction. So we're supposing that this person here, this person, and this person haven't yet been detected as person objects. So for now we have 1, 2, 3 persons who haven't been detected. So in that case we have 3 false negatives. So that's why we have 1 true positive, which is this, divided by 1 plus 3, which is 1 and 4. We move to the next person. Moving to the next person, we have 2 false negatives, because this other false, initially false negative, now turns into a true positive. So we have this true positive. We see we go from 1 to 2, and then the false negatives now only left these 2 persons right here. And then finally we have this, where we move to this other prediction right here. Now this prediction actually isn't a true positive, hence we have this 1 as a false negative and this as a false negative. So for now, again, we still have 2 false negatives and 2 true positives, hence our recall is 2 and 4. So from this we could plot a precision recall curve, and it's actually the area under that curve which is considered to be the average precision. Now let's do that plot. We have from 0 to 1 precision, and then recall year. We have this point, next point, this is a point 1, 0.25 right here. Next point 1, because this is 1, 0.5 right here, and then this other point 2/3, that's 0.66, 0.5. So these are the different points, and then once we link them up like this area under this curve is considered to be our average precision. Now if we have to calculate this area under this curve, we will have to find the area of this rectangle. Now what's the length of the rectangle? From 0 to 1 we have a length of 1. What's the width? The width is 0.5, because from here to this point is 0.5. 0.5 times 1 gives us an area of 0.5, hence our average precision for a person is 0.5. We now move to the aeroplane. For the aeroplane, we have the precision, or we start with this first aeroplane right here. True positives equals 1. The false positives equals 0, because we don't have any false positive for this first one when we're considering that we're just working with this first image. So there we have a precision of 1. Now we'll move to the recall. For the recall, we have false negatives that equals 1, because we have this aeroplane which hasn't been predicted, or which hasn't been located as an aeroplane. So in that case we have a recall of 1 divided by 1 plus 1, which is a half. Again, we have this precision recall curve which we plot like this. We have this point here, the point 1, 0.5, and that's it. We find the area which again corresponds to 0.5. So this means our mean average precision will be 0.5, because 0.5 plus 0.5 divided by 2 is equal to 0.5. So right, with this, if given many more classes and many more images, we just repeat this process. Let's take a more general example. Supposing we have this kind of PR curve, precision recall curve. Now here we have y, x, and then we have these different points like this and this. Okay, then we'll link them up like this, and then we have this area under the curve which we have to calculate. One way we could do to find this area is by dividing it into several portions, like into these two portions where we have this rectangle and this trapezium. For this rectangle, we simply have 0.5 times 1, so we have 0.5 for this area. And then for this area right here, we have half times the sum of this parallel sides as the sum of this side, which is 1 plus 0.6, because the y coordinate is 0.6. So 1 plus 0.6, that's 1.6 times the height. So we have half of the sum of parallel sides. Half of 1.6 is 0.8, and then this height here is 0.66 minus 0.5, which is 0.16. So 0.8 times 0.16 will give us 0.128. Now if we have 0.128 plus 0.5, we get 0.628. But this method can't be automated very easily. So what we'll do is we're going to use the shoelace algorithm, or the shoelace formula. According to the shoelace formula, which actually is the area of a polygon, because basically we could create this, or we could create a polygon from this, where we have this going like this, and then we link it up with the origin right here. So we'll link all of this, and then we'll find the area of this polygon. And according to this formula, we have the sum from I equals 1 to n minus 1 of xi yi plus 1. So if you consider this to be x1 y1, x2 y2, x3 y3, x4 y4, x5 y5, and x6 y6, then we'll be summing x1 times y2 plus x2 times y3, and so on and so forth. Then at the end we have plus x6 times y1. So that's what we do here, minus x1 yn plus the sum of xi plus 1 yi from I equals 1 to n minus 1. Then after this we find the absolute value and then divide by 2. Now running this formula, we have this exactly x6 y1, because n in this case is 6, since we have 1 2 3 4 5 6 points. Then x1 y2, that's xi yi plus 1, since I is 1, x1 y2, x2 y3, x3 y4, x4 y5, and x5 y6. Then minus x1 y6, then here x2 y1, x3 y2, x4 y3, x5 y4, and then x6 y5, and then take the half, or we halve this. Once we do this, or once we compute this, we should get 0.628, which is very accurate. Now note that you don't have to forget to include the origin, because if you don't include this origin, it's going to be this polygon instead. We have this, and it's going to try to link up with this. So we're going to have something smaller than the polygon we're trying to calculate. So that's what we're going to do. Let's now go ahead and implement the mean average precision performance metric. To do that, we shall make use of the outputs we got from here. So basically we'll get this output, but we shall not be needing this part where we actually draw the bounding boxes on the image and show the image. So what we do here is we have this function generate output, which gets a test image and does the same as what we have here, and then we output the boxes after the non-max suppression. So we could run this, and then once we have those boxes, we could now get into the mean average precision calculation properly. Note that there are two helper functions which we shall build, or two main helper functions. That is the calculation of the IOU between two boxes and finding the area of a polygon. So right here we have the IOU function, which takes in a box 1 and a box 2. That's a bounding box actually. Now each of these have a mean and max value. So basically B box 1 is made of x mean, y mean, x max, y max, and then b box 2 is made of the same x mean, y mean, x max, y max. Now to better understand how this IOU is going to be calculated, we're going to use these two examples on the slides. We recall that the IOU is the intersection divided by the union. So if we have this example, to get the intersection, it suffices to get this point and get this point. But then what is this point? This point is the maximum of these 2 points. So recall, we could have this point, we could call this the means, and then there's the max. So if we have a box, suppose we have a box like this, these are the means, or this is the point mean, and then this is the point max, where this means this point mean is made of x mean, y mean, and then this x max, y max, which we could obviously use to compute the area of this box. Now right here, to get the area of this box, it suffices to get the max between x mean and y mean. So if we have x mean, y mean, max, the max between this, for the x mean, the max is obviously this. If we're considering that our reference is a certain origin, say up this way, so this is going to be our x mean, our x mean max, and then this is going to be our y mean max. So this is the point we're dealing with. Now for the maximum, to get the max right here, we get the minimum of the 2 maximums. To get the minimum of the 2 maximums, we get this. So if we try to get this minimum, we're gonna get this point here. And obviously once we have this point and this point, we could calculate the area of this box very easily. Let's take this other example. Supposing we have our origin. Recall the origin we're working with when dealing with this object detection algorithms. If our origin is somewhere like this right here, we'll have that the max between these 2 is going to be this right here. If our max is this, so even if this box we have now is this one, and then this box is this one, you see that once we follow the rules, we'll always get the intersection very easily. The max of the 2 means, or the 2 means like this and this, if we try to get the max of the 2 means, then we get this point. If we get the mean of the 2 max values, then we get this point, and obviously with that we get the area of this box. Let's take a third example where we have this box, this one, and then this other box right here. To get this point here, we get the max of the 2 x means. Now the max of the 2 x means coming from this direction is clearly this x mean, and then the max of the 2 y means is clearly this. So that's how we fall on this point right here. So note that you could have the max of an x mean coming from one box and the max of a y mean coming from the other box, like in this case right here. So once you follow the rules, you just fall on this point. Now the mean of the x max, so if we come from this point, the mean of the x max is going to fall on this box, and the mean of the y max will fall on this other box. So we are at this point right here. Now with that, we could get this intersection. To get the area, that's the union. To get this union, what we do is we get simply the area of the box, because for box 1 we know it's mean and we know it's max. For box 2 we know it's mean and we know it's max. So to get the area, we get this max of this area for box 1, and then to get for the box 2 we get this own area. We add the 2 and then we subtract the intersection simply, and that's how we obtain this A union B right here. Because if we just take this and then, or if you take this box and we add with this box, we're going to be calculating this intersection twice. So what we do is we subtract the intersection to obtain this new shape. Given that that has been understood, we see clearly here that we have the maximum. We could use TF, the maximum. So that's fine. Okay, so we have this maximum of the means. So here we're comparing the x means, and then the maximum of the y means, and then the minimum of the x max, and then the minimum of the y max. So that's how we obtain this new box, which is actually the intersection. Now to get the area, we simply have this x max minus x mean times y max minus y mean. And that's exactly how we have this x2 minus x1 times y2 minus y1. Now note that if we have negative values, we'll take this to be 0. So that's why we have the maximum between this and 0. So in case it goes negative, we'll choose 0 instead. So it just tells us that there's no intersection between the two boxes. Now let's go now into calculating the union. To get the union, we get the area of box 1. We see we still have the same here. We have x max minus x min times y max minus y min. For box 2, x max minus x min times y max minus y min. And then we get the area. To get the area, we have the sum of the two minus the sum of the intersection, as we could see right here. And then the IOU is a intersection divided by the union. So basically that's what we get. We just return this right here. So that's fine. We run it. And we could also test this with some values. It's always very important to test such methods before using them. So let's take the values we had in the notebook. We have this points 1010, we have the points 1515, the points 2020, and the points 2525. If you look at this first box, you'll see that we're going from 1010 x min y min to 2020 x max y max. For the second box, we have 1515 x min y min and 2525 x max y max. Now to compute the union, we could see clearly from here that we have this is 10 by 10 box, because going from this point to this point is actually from 10 to 20. So this is a 10 by 10 box, and this too is a 10 by 10 box. So we have 10 plus 10, that's 100, actually plus 100, 200, minus this interior right here. Now to get for this, it's actually a 5 by 5 box. So we have 25 divided by 175, because 100 plus 100 is 200 minus 25 gives 175. So we have 25 divided by 175. We have from here 25 divided by 175. We see we have this value. Now let's run this right here. We're told this is not correct. Let's take this off, run it again, run that. You see that we have exactly the same value. That tells us that our IOU calculation is accurate. Now the next calculation we shall do is to find the area of a polygon, the kind of polygon we have, or the kind of polygon we had seen in the slide. To compute the area of polygon, we use the same formula we had defined in the slides. So here we have the area 1, and then we have area 2, where area 1 corresponds to this first calculation right here, and then area 2 to this calculation. So we have area 1 minus area 2, the absolute value, and then times 0.5. And that's exactly what we get here. Now for area 1, we're basically applying the formula, so we're simply adding up these values. That we're doing the summation of xi times yi plus 1, and then we finish up with x, the final value, times the first value of y. Then here again we have xi plus 1 times yi. Then we finish out with the first value of x times the last value of y. So basically that's it. We could run this, and then we could test it actually using the same points we had in the slides. So run this, and there we go, we have the same answer. Let's now dive into the code of the mean average precision. As you could see here, we have this loop where we go for each object class and classes which we had defined previously. We're going to calculate its own average precision. Now let's get into one class. We start with this precision to be 1, that is, we're actually declaring a list which will contain the different precisions and the recalls. The reason we start with this 1, the point 10, get into the slides. As you could see right here, we had this precisions and recalls which we pointed out in the plot. As you could see, we had this 1, 2, 3 different points. And to compute this area under the curve, we actually link this up with the y-axis. And also we also have this link with the x-axis, since it's basically a polygon's area we're trying to calculate. And then we add this origin. So that's why we start with this. That is, we'll start with this point. We suppose our list of precision and recalls starts with the points 0, 1, where the recall is 0 and the precision is 1. And then we now move ahead to do these computations to keep on adding up this into that list, such that we could now get the area of our polygon. Then we define this variable number of class, which is initialized to 0, which is used in computing the recall values. The number of true positives and false positives initially are set to 0. Now let's see how we compute the number of class and why it is even useful computing that. If you notice in the slides, we didn't actually need to work with the false negatives, because at each time we'll always have a fixed number at the denominator when calculating this recall. Now this number corresponds to the number of times that particular object is in the different images. So in the object person, for example, occurs 1, 2, 3, 4 times. So it suffices just to calculate the number of times we have this object in all the different images and then use it as a denominator for the recall, such that once we're working with the precision, all we need is the true positives and the false positives, knowing that we're going to use the same true positive here, the same true positive here, the same true positive here. So that saves us the stress of trying to calculate the false negatives. Now once we know this, as you could see right here, we go through all the images in the set we're working on the validation set so that we could test this very quickly. So we have the val images and the val maps. Now what we have done here is we get the actual target labels, and that's because we're actually using this target labels, that is those labels in white. Like you see, for a person we have this one, this and this. If we're the precisions, or if we're instead the predicted labels, then we should have a value of 3, because here we have 1, 2, 3, so we will have had 3. But since we're working with the targets, it's 1, 2, 3, 4. And let's now define this target. Let's insert a cell below this. We have that. We have our target function, our get target function, which basically is what we've done already. The only difference here is we have this generate pre-output. Now the role of the generate pre-output is similar to that of generate output, with the difference that we are actually not interested in converting this into a trainable output or into the output that gets into our model. All what we're interested in here is getting the x mean, y mean, x max, y max values, and then putting it in this new reference of our input dimension. Now our input dimension we have selected from the, or we have set from the beginning, is 224. So we're leaving from width of 500 to that of 224, height of 281, for example, to input dimension of 224. So basically what we're doing here is we're getting the actual x mean, y mean values, and not interested in converting this into this form which we have seen already. And so that said, we're able to get now the different bounding boxes. So this permits us get all the different bounding boxes. We've also made a modification on the pre-processed XML. As you could see here, we pass in this map argument to say that when we calculate the map, it should return values different. And the reason we're doing this is because we're not interested in dividing the values for the width, or dividing the values for the x mean and y means by the width and the height before passing in. So what we do here is, if map, that we've added this, by default is false. If map, we have this, we multiply it back by the width we had done here, so that we get actually this initial value, which convert it to an int. And for y mean, we repeat the same process actually. Now at the end, we don't return the bounding boxes, we return the bounding boxes, and we also return the height and the width of the image, such that we could use it in this generate pre-output function in computing the y target. Recall that we got the height and the width of the image using this actually. So basically that's the reason why we need to get this. Now once we have this bounding boxes, which come with the classes that's at the last position, we are able to say that, okay, for a given object class, if the target corresponds, that's for a target in the y target, as we have a certain number of bounding boxes, and so if there's that correspondence between the class and our current object class, the number of classes goes up to 1, or increases by 1. So for example, yeah, let's have this. Let's print out the Y target. We could comment this part. We now run the mean average precision, and there we go. We see that for each of the images we have the target object. So like here, for example, we have aeroplane, aeroplane, person, person. We have aeroplane, 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 and so on and so forth. So for each of the images we have now the Y target, and we're just simply going to go through all these different targets. And the reason why we have this repeating over and over is because for example, for each object we repeat the same. So what we'll do is let's take a break from this for loop. So once we get into this, we should take a break so we could see that clearer. Okay, so we've taken the very first object, and then this is what we get. We have this Y targets, basically this, and then we now go through each and every one of them. We compare the target 4. This is target 0, 1, 2, 3, and then this is target 4. We compare this target 4 with the object class. If that is okay, we increase the number of classes. So in this case, normally we should have number of class. If we print out number of class, let's say we return n class. If we return n class right here, we should have a 0. You see, that's because our first class is actually a background, so we don't have any value to put out there. Now let's do this. Let's say we print out the class. That's for each object, the n class, the number of times we have that object. We could actually change this to number of objects, but that's fine. Let's leave it at that. So we have this print of number of class, and then let's take off this break, run this again. You see that here we have 0. Now for the aeroplane we have 5, because for the 2 images we have in our validation, we have this aeroplane 1, 2, 3, 4, 5. So basically it counts all that. And then if we go to the place where we have person, we have here, you see we have 2, because that gives us, for example, person is 1 and then 2. The next image has nothing, so that's it. We just have this 2, so that's fine. So that's how we get this number of times we have that object, and that gives us the denominator of the recall. So with this we could take this off and then go ahead to uncomment this section. That's fine. Take this off. Okay, so let's get into the calculation of the precision now and the recall too. So we have, again, for this image we get the Y target, that's the actual values. We get now the predicted values using our generate output function, which we have defined from here. The generate output function, which takes a test image and then generates the output according to the model. So once we have that, our generate output, basically we're using this. So we're going for each and every image, we're generating this output. Now we'll say, okay, for each predicted output, like here in the slides, for each of these predictions, we have to compare and see whether there is a box or an actual box, an actual target box whose IOU corresponds to a value of greater than 0.5 and which has the same class with this predicted box. So what goes on here is we have for pred and Y pred, if the classes match, that's, or rather if the classes don't match, so if pred 4, again we have like target 4, if pred 4 doesn't match with the object class, then we pass, that is we don't work on that prediction again. Now if you have this pred 4, like if you confuse why we have that, you could get back to this where we had this final NMS boxes. This final boxes right here had the positions and then ended up with a class, so that's why we have pred, we compare with pred 4 right here. So let's get back to this. So we're comparing, if they don't match we pass. Now if they actually match, we suppose that the false that is not yet found. And now for each target we are now comparing the pred 4 with the target 4. So we're comparing, we make sure that the match, there's a class match, and also that the IOU between the predicted box and the target box is greater than 0.5, or that's a threshold which we had defined previously. So let's say 0.5 right here, that's fine. So we're comparing that, And then if that is true, that is if all the conditions are verified, then found turns to true. This found, which was false, now turns to true. We break out of the loop because we've already found this target, or we've already found a target that matches with a prediction. We break out of the loop and we move to the next prediction. Now if those found, as if we have this, that if this condition was verified, then we increase the true positives. In the case where it's not verified, we increase the false positives. Now if this is greater than 0.001 and the true positive, that's, we're comparing the precisions with 0.001. we're avoiding the case where we have precision 0 and then recall 0. That's a common bug we may have. So if this is greater than 0.001 and this greater than 0.001, then we add this to the precision. Basically we're adding this true positive divided by true positive plus false positive to the precisions, and then the true positive divided by number of class, which we had calculated previously, to the recalls. And then we repeat this for each and every image. So basically we do this for all the images. And then lastly we add the 0 max recall point. To better explain the 0 max recall point, recall that we also had this 0.1 point that was here. We had actually 3 points. We linked this to the y-axis on this, and then to link this to the x-axis, because it's actually an area, because if we don't have this, if we don't link this, what we'll be doing is that since it's a polygon, we'll have this, 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 and then it's going to look for this path like this. So instead of missing out on this area, we have to make sure we come right down to the x-axis. And to get right down to the x-axis, it suffices to look for the maximum of all the recalls. And for now, the maximum of all the recalls is 0.66. That maximum of the recalls and the precision at 0. And that's why you see here we add that precision 0 recall at max recall, so that we have that complete polygon. And then we add the origin, and that's fine. So once we have this, now we use our area polygon function we had computed to calculate the average precision for a particular object. And then we have the average precisions now, which is for all the different objects. So we could have this, run that, and here's what we get. We see that we have for each object, like say for example for the background, we have an average precision of 0. For airplane, we have an average precision of 0.69. For persons, 1, but for the rest is 0. And then the mean average precision now is 0.07. That mean average precision is with an IOU of 0.6, or rather 0.5. So we could modify this to say an IOU of 0.99, and then we should know there's a difference. Note that here we had 0. This, so we could have this. We'll run it. Notice how the mean average precision changes depending on the IOU threshold we select. So here we're very, very strict on this. So that's it. Run again. And that's all about this section. We've succeeded in computing the average precision for each object and then the mean average precision. Now this mean function is basically a function like this, which takes in different values, does a sum, and then divides by the length of the value. So this is a trivial function to compute. Suppose we have a, which is, say, or let's just calculate the mean directly. So we have the mean of say 2, 3, 4, 5, or say 6. Here we have 2 plus 3, 5, 5 plus 4, 9, 9 plus 6 is 15, 15 plus say 5 is 20. Now 20 divided by 5 should be 4. So that's a mean. And with this, we're done with this section. See you in the next section.